Least squares are one of the methods of optimization to reduce the error when we try to do our linear regression. As we can see, some of the errors could be positive, some could be negative, and the idea is to minimize this error. Okay, so in this case, the error I will be the difference between the expected y in, let's say this is the y I, right, that we are expecting, minus the value that we fit here in the linear regression, right? In this case, we say that this linear, this line, it is represented by this formula. Okay, so it will be xi. This is my xi, right? Something like this. And if we substitute, we remove this parenthesis, we have yi minus a0 minus a1 xi. Okay, so the sum of the square is a way to avoid the problem that we have with different signs, that if we have positive here and negative here, it could be very possible that the sum of them is 0, and that is not true, right? So one thing that we can to avoid this is to square the error. In this case, if I have the sum of the square of the error, we'll have the summatory of n I equals 1, right? Which is the same if we write this in this form, as we have it here, y is 0, a1 xi, everything to the square. Okay, now what? We know that the tendency of the error is to go to infinity everywhere. So if I move this to one side or the another, the error will increase. So, but at some point it will have a place where the error is minimum, right? I am putting this in two dimension, but basically this is, in this particular case, is like in 3 dimensions basically, and we have to find the bottom of this surface. In this case, we have to apply the derivative for x and the derivative for y and so on. So for this we have, in this case, x and y is a0, a1, because these are my variables. This is and the constant numbers that I have to put it here, but because I don't know which numbers are, these constant numbers are not constant, are right now are variables that I need to figure out what is the value whenever this point is minimum, right? So the partial derivative of the sum of the squares of the errors with respect to a0 must be equal to 0, right? The same thing we have to do for the partial derivative of the sum of the square of the errors with respect to a1. Okay, must be 0. So for this we have to calculate it like this. We have still the summatory that is going to end from I equal to 1. In this case, these two will go down, right? We have the same thing internal. Right, and we have to, we are calculating with respect to this variable. So the only one that I have this variable is this. Everything else is a constant for this type of derivative. So we have to multiply by -1. and this will be equal to 0. Same thing we do with respect to A1. We will have A1, we also move the 2 to down, the same thing. And then the only one that we have it here is this, so everything else is a constant, so we have to multiply by minus xi, okay, equal to 0 too. Then if we move this one internally and we also distributed the summatory, we will have the formulas like this, right? 1 is 0 plus summatory A1 xi, right? This one will be negative, right? Because it's negative, we can move this to the other side and will be positive. Right, I. The same thing for the other one. See, these two, we can move it outside of the summatory, and because the other side is 0, it doesn't matter these two, so we will get 0 too. So we have this I 0xi plus the summatory and this I to the square equals 2 n I1 x I y1. Okay, so for this, if we can see, we basically have a matrix here, right? This value indeed is equal to n a0, right? Because this is a constant, it doesn't have any xi anywhere, and we can put this as a matrix in matrix format, right? Something like this. We can even move these two outside, something like we have n summatory 1 xi, we can have xi and square, right, because this is a square, multiply it by the vector a0 a1. You know, if we multiply this, we will have the same matrix that we have here, will be the same, or this will be the same basically. Now what if we solve the matrix to get the values for a0 and a1? We will have something like this. Basically, we will have the formulas that we know for the linear regression, which are this, right? And multiply the summatory I minus divided by, again, the same thing, the summatory 1 x squared minus, in this case, this is where most people make a mistake, this is the square of the summatory, which is different from this one. Okay, this is different from this one. These are two different terms. This is the square of the whole summatory. This is the summatory of the squares of the point. Okay, and A0 will be summatory 1 of y divided by n minus the value, this value that we have here, by the summatory xi n to 1 divided by n, and this is actually the average value, right? The mean, the arithmetical average. Same thing for this one. So A0 will be the average of y minus wherever A is starting at the average of x, right? This is the way that we do for two dimensions. Now what? Let's see what happens when we make it for more variables. Let's say we have a generalized linear regression. In this case, we will have more x. Previously here we only have one x, right? One x and one y per x, right? This is just 2 dimensions. But now let's say that we have many y2 and right, which is the result of this is the matrix that is resulting matrix of n 0 x 1 to 1 and so on, x 1k, right, x to 0 to 1 to k, and so on, x and 0, and finally the last one, n k, right? And this multiplied by the vectors of the variables that we don't know, right? Let's say b0, beta 1, and beta k. I have to put it this because this is estimated, plus what? Plus the error. Remember that this value that we are trying to match is wherever we are calculating plus the error, right? So we need to also include here the error vector, right? 1, the error for 2, and the error for n. Okay? So in this case, the sum is a vector sum. The sum of the errors is the vector sum. This is the sum squared of the whole vector, right? Plus square 2 plus all this, right, to the m. Then we will do n the square, and because this is a vector, basically the square of a vector, how can we get the sum of the square of a vector? We have to multiply by itself, but because they will not match the columns and rows, we need to do the transpose. So we have to do something like this, transpose, right? So this is the sum of the square of the vectors in this case. And we have to optimize that, right? So what we should do next, let's say if we have that my error is equal to the vector, this is my vector y, right, minus my matrix X, this is my matrix X, multiply by the vector of this one, right, of betas, all the betas. So if we basically what we did here is we move everything to the other side and we get along the errors. So with this we do exactly the same thing for that we did previously to do the optimization. First we have this error that we say that is transpose, right? It is the y x beta, the vector transpose multiply by exactly the same but as it is, right? And then what? This transpose could be propagated internally of the parentheses. We do the multiplication like in algebra, in basic algebra, and we will have something like this. Minus, because this is exactly the same, we have the 2 times the same thing here, beta transpose, right, x transpose y, the vector, right, plus beta here transpose x beta, the vector beta, which is basically this for this, right? And then what? We have to calculate the partial derivative of the error, the sum, the error square, with respect to all the variables in the vector that we have here. So the same thing, we have this minus 2 here, this doesn't have any beta anywhere, so keep it the transpose of the matrix X by the vector Y plus X this is also 2 because we have 2 of them, we have this one and this one, by the vector beta, we just remove one and we keep it the other one. This will be equal to 0, and then we just move these 2, we can simplify these 2 and get rid of these 2, right? And then we have x, this one, right? Because this is negative, we can move it to the other side. Beta, vector beta equal to this place, to this part, right? And now we cannot divide a matrix, but we can multiply by the inverse, right? So if I multiply by the inverse, this will be equal to the identity matrix Now we will have this x transpose x minus 1 multiplying x transpose y, right? And this will be the identity matrix. So we have this beta vector, that is the variable that we want to figure it out, will be equal to transpose, right, x minus 1 multiplied by x by the matrix x t y's. And by the way, this part that we have here is called the pseudo-inverse. Okay, so there are two ways to calculate these squares. One for the single two variables and the other one for a full matrix for generalized linear regressions, for example.